This is section 13.8, and this is our very last example in this chapter. This is example 3. So we're going to calculate this surface integral by using the divergence theorem. And in this case, what we have is actually 4 different surfaces. So if you look at the diagram here, if we were to do this using techniques from 13.6, we would actually have to do 4 separate surface integrals, which obviously would be very, very time consuming. One surface integral for every one of the 4 surfaces. So the divergence theorem, even though this problem is a little bit lengthy anyway, the divergence theorem is a huge shortcut and a benefit to us. And remember, each one of these 4 surfaces, it borders in total a 3-dimensional object. So we're able to use divergence theorem due to that enclosure. And our first step here is that we're going to take a look at the divergence of f, and we get y plus 2y plus 0, so we end up getting just 3y, which is nice and simple, which is good. And so we have the triple integral over E, and remember E is that object that's being formed of 3y dv. So our next task is to figure out the dv. What do we want in terms of order? Do we want dx, dy, dz? Do we want dy, dx, dz? All the different renditions of that. There's basically 6 options that we could do. I think with x, it's probably easiest to start with that on the outside. This is all stuff that we did in chapter 12. So this is not chapter 13 anymore. Honestly, chapter 13 is done. The red stuff is chapter 13. We use divergence theorem. Now we just have set up our triple integral, and now we go from here. So if we let x go from -1 to 1, let's do maybe z on the next integral. So z minimum is 0 on the xy plane. We're told that. And the maximum is 1 minus x squared. It's that surface right here that kind of is the upper boundary of z. And then our next integral would have to be y, which goes from 0, and then it goes to this plane right here, 2 minus z. And we still have 3y, and then we have dy, dz, dx. So again, there's other renditions of this that we could do, but let's go ahead and go with this one and see where it takes us. So we're going to start with the antiderivative in terms of y. So we have the integral -1 to 1 and 0 to 1 minus x squared. And we have 3 over 2 y squared. And y is going to go from 0 to 2 minus z. And what we get then is 3/2 of 2 minus z squared. That's going to be 3/2 times 4 minus 4z plus z squared, and we still have dz, dx. So just to simplify it one step further here, we have 6 minus 6z plus 3/2 z squared. Okay, so we've gone from a triple integral, we've made our way down to a double integral. Now the antiderivative in terms of z. So I'm going to pause this one. It's a little bit lengthier, and I'll come right back in a minute. Okay, so here's our antiderivative. It's kind of an ugly one. So we just want to expand everything. There's this cubic here, which just adds complication a little bit. So we have all of our different terms. Combined like terms, we have this integral. We can actually speed this integral up a little bit because if you notice, all of these elements are divided by 2, so we can actually pull a 1/2 out. In addition to that, this particular integrand is actually even, which means that we could pull the 1/2 out, then we can multiply by 2 and let the integral be from 0 to 1 because it is even, and that will save us a little bit of time. So the 1/2 and the 2 end up canceling in the front there. So that's, I don't know, a little bit simpler, a little bit faster through. So we'll just stick together and finish this out. So we have 7x minus x cubed minus 3/5 x to the 5th minus 1/7 x to the 7th, and then we're going to evaluate from 0 to 1. So we end up getting 7 minus 1 minus 3/5 minus 1/7. And then if you use a calculator to simplify this down, you get 184 divided by 35. So there we go. That is our final answer and the last example in chapter 13. Well done.